In this video series, we're talking about research designs and the general linear model. And in the last video, I looked over the research design. Now we're going to talk about the general linear model, that is, how we actually analyze the observations that we obtain from our design. The general linear model is a model of a participant's responses as a linear combination, that is, a sum of factors and/or covariates. That is, we're trying to explain what we observed as a relation to what we actually set up for our factors and covariates in our design. So we have explanatory factors and/or covariates. We could have interactions among these explanatory factors or covariates. But as it turns out, those two things, albeit the only two things that are in our design for explanation, will not completely explain our observations, and that's because all the participants in our study are unique. So when I create this linear combination or sum, I have to have these three things. I have to use, obviously, what I'm trying to use as an explanatory factor or covariate, how I'm trying to explain the response. Then I have to consider whether there's interactions among those. Now I say I have to. I might theoretically say that there is no interaction, and so therefore I do not put it in the model. But it is one of the potential explanations, is an interaction among explanatory factors, because explanatory factors, when summed together, may not actually provide for us all of the effect on the response. You may have to look at them in combination, and that's the interaction. And then I have that third piece, which I can't explain in my model, and that's the uniqueness of the participant. So I'm going to put that in my model in order to explain everything, although that uniqueness part is not part of the research design. It's something I actually wish wasn't there, but it has to be there. We'll look at that in a moment. The model is directly linked to the chosen design because it tells us the number of factors or covariates. It tells us the types of factors or covariates, and it tells us how we measured our response, whether in fact we put individuals into categories, in which case we'd have to switch to the generalized linear model, or whether we had individuals measured on a quantitative response. So the model is directly linked to the chosen design. This is it. This really encapsulates the general linear model, but to make more clear how this all works, we should look at some examples. Let's begin with the one-factor randomized design and model. Participants are randomized to J different experimental conditions. So if we have just a treatment and control, capital J is 2. If we have a treatment, a control, and a second treatment, capital J would be 3. So J is the number of different experimental conditions. Each score is then portrayed down here in this model as each score is portrayed as the sum of the mean. That is, we use this as the baseline. That's rather arbitrary, but it's become convention to use the mean, not 0, as the baseline in our model. Then there's an effect of the condition. So we're indicating that with the Greek letter alpha, and notice the J down here is a lowercase j. That's a subscript indicating what condition we're talking about. So if capital J up here can be 3, meaning we have 3 possible conditions, and we're focusing on someone in condition 1, then this lowercase j would be 1, and we'd be talking about alpha 1. And then the residual, that is the uniqueness of the participant. This leftover piece cannot be explained by the model. So really, the element of the model related to our design is our response, our baseline, and our effect. This was not in our design, but if we're going to truly explain the observations we make, we're going to have to put this unique piece in here. Notice the unique piece has an I indicating which individual we have in our study. So if we have 15 individuals and I is 3, that means lowercase I, we're talking about the third individual. And again, the lowercase j is what condition is that third individual in. Similarly, the I subscript up here will be the same as the I subscript down here on epsilon. This I subscript indicates the individual number, and the j again indicates what condition they're in. So this model is meant to completely account for the observation. We're in essence partitioning this observation as a sum of the baseline, the effect of the treatment, and the effect that's due to the individual, that is, the part that's not in our design. So to understand this further, let's go on here to the next slide, and let's take a look at an example with Dr. Frankenstein's monsters. Now, why Dr. Frankenstein's monsters? Well, that takes the human characteristic out of it for just a moment. I'll come back to humans in a moment. But for now, whenever Dr. Frankenstein creates a monster, the monster is going to act the same as every other monster. That is, these monsters are clones. They're all built the same. Each monster behaves the same. And so in that case, we have the simplest possible model we can have. That is, the observation we make for the ith monster, let's say we have 10 of them, the observation we would make for monster 1 is the same as the observation we make for monster 10. All of the monsters have the same value, so all we need to put in is that mu, that mean, that baseline for each of the monsters. So let's suppose that we take our monsters, in this case I have 14 of them, 14 monsters, and I teach them a unit on human history, and at the end of the unit I administer a 50-point test, and all monsters score a 38. They're all going to score the same because each of these monsters are built the same. They're clones. So it's like having the same person repeatedly in your human history class. Everyone ends up with a 38. Now, because there's the potential to have many, many, many more monsters, this is considered a sample, so I'm putting a hat on the mu. The hat is going to stand for an estimate. And when we have a sample, we're using that as an estimate of the population. Now, the fact here in this example is because all the monsters we would ever build are all going to be the same, the sample estimate's going to equal the same as the parameter for the mean, mu. But that's not the way it's going to be with humans, so let's go ahead and put that hat on there. Mu hat, our estimate of the population mean is 38 based upon the mean of our sample. We're observing for each of these monsters a 38. Now, why do I have a hat on that if it's an individual monster that I am observing? Well, the fact is that if I were to do this with the same monster on a different day, I might have gotten a different result. Or maybe I did it with a different instructor for the human history class. I would get a different result. That is, the observations that we obtain on any given day and in any given administration of a test for a person, we do not consider as an absolutely correct observation of what score they should get, what measurement experts will call their true score. It's not necessarily going to be their true score. In fact, it's likely not going to be. So we're going to put a hat here because that is our best guess of their achievement. It is the actual score they got, 38. But keep in mind that when you get a score on a unit of human history, you're not interested in the score per se. You're interested in achievement of knowledge of human history. And the test is an imperfect way to obtain where someone is on their understanding of human history. So the hat makes a whole lot of sense. Notice the I can vary from 1 through 14. Mu is fixed at 38, but the I can vary 1 through 14, and the 38 that we get here is the same for both the mean and the individual monster because all monsters gave us the same score. Now let's do an experiment with Frankenstein's monsters. Now let's assign them to experimental conditions. And our primary interest in creating this design, which is a one-factor randomized design, our interest is in determining if there's a different effect for each of our experimental conditions. So we're going to assign monsters to experimental conditions. Every monster within a given condition is going to behave the same as all other monsters in that condition. However, because monsters are in different conditions, they're going to learn different things. They have different teachers. They might meet different times of day. And in fact, they're going to get a different intervention. That's the whole purpose of creating this experimental design. So now I've introduced into this not only a baseline or a mean, but I've introduced into this an effect that's due to that particular condition that the monster's in. We're calling that effect alpha, and there are J conditions, so each condition's going to have an effect. And we're reflecting that each monster is going to be in one and only one of those conditions. So let's see how this works out in terms of actual data. I still have my same 14 monsters, but now when I teach them a unit on human history, half of the monsters are aided by frequent concept mapping. So that's this group over here, this second group. They're going to be aided by frequent concept mapping, where the other monsters don't get that concept mapping. They are still taught the same material on human history, but there's no concept mapping. And in fact, we want to make these conditions as alike to each other as they can. Perhaps use the same instructor in both, the same textbook for both, the same instructional time of day for both. We're going to try on as many of the possible extraneous variables as we can match up to match those up, except we don't want them to be the same on concept mapping. We want one group to have no concept mapping and the other group to have concept mapping. And so our hope is that we can then ascertain the effect of concept mapping. So let's see what we get. If you were to take those 14 scores and average them, you would get an average of 42. So here my best estimate of the population mean is 42, the average of all the scores, and that's now going to be my baseline. What is the effect of no concept mapping? The effect of being in the no concept mapping, which again is an estimate because I'm not using all possible monsters there. I haven't used the ones that are over here in concept mapping and the no concept mapping. I've only used these 7. So I have a hat on this. My alpha hat for the first condition is -4. Why? Because 38 is 4 below 42. Now, does -4 mean that being in the no concept mapping group was negative, was detrimental to these monsters? No, it's -4 relative to the baseline of 42. If we had used as a baseline 0, well then these monsters would be 38 above 0. So really, whether you get a negative or a positive number isn't indicating whether or not there's any effect of being in that condition. It's indicating what that effect is relative to the average. So these monsters are 4 below average, whereas on the 46s with the concept mapping, 46 is 4 above 42. So these monsters have this effect of 4. So again, both units, they learn human history. So this negative doesn't mean they didn't learn human history. It means they're 4 below average. And why are they 4 below average? Because we have a concept mapping group that did quite well. They did 4 above average. So right now, if I look back at this model I had, the model was that an observation for a monster is equal to baseline plus the effect. So if you look back here, what I end up with is, if I'm looking at the first 7 monsters, so I is 1, 2, 3, 4, 5, 6, or 7, any of those, that I start with a baseline of 42, -4, which is my alpha. Notice I'm putting together the mu with the hat on it and the alpha to match up with this equation here. And so I have 42 -4, which gives me 38, and that's for the first 7 monsters. Once I get to monsters 8 through 14, so the I becomes 8 through 14, and the J would be 2. I notice here that here I had the J, but I didn't put it up here. This would be YI1, and this would be YI2 for the second group. Here I have 42 plus 4 is 46 for the 8th through 14th monsters. So we're modeling each observation as a component of the baseline and the effect relative to the baseline. So that's that model. Now, the problem is we work with humans. We don't work with monsters. So let's do the following. Let's now give each monster an individual and independent personality with free choice and too many factors to account for in experimental settings. In other words, let's instill in the monsters human attributes. And if we instill in the monsters human attributes, we have to now recognize that there are going to be effects that are not included in our original model that we had back here. Back here was our original model that we wanted to use, but now we have to account for the fact that we're going to have things not in that model, and we're going to put it in now as error or residual. That is, the alpha is what's of primary interest here. I want to understand the effect of being in that treatment condition, but that's not going to tell me everything about this score, so I have to put in an epsilon. So let's look now at these new monsters who have individual personalities and free will. And now we have the no concept mapping and the concept mapping. I arrange these scores so I still get a mean of 42. I still get an alpha 1 being in the no concept mapping as an average that's 4 below. But notice it's not 4 below for everyone. It's an average of 4 below. And here the concept mapping is an average of 4 above the mean. But now when I start looking at the individual monsters, like if I look at that very first monster, monster 1, which would be y hat 1, comma 1, because they're in the first group. If I look at that first monster, we start at 42, notice the model again, mu plus alpha plus epsilon. So we start at our estimate of the baseline, 42. We take minus 4, which is our estimate of the effect of being in the no concept relative to the baseline, but that would give me 38. And this monster's actually, this 41 is 3 above 38. So even though this monster would come down as a result of being in the no concept mapping group relative to baseline, the monster actually scored higher than I would have predicted for that monster. And that's the part that I cannot account for. There's something about that monster's intelligence or the way they take notes or the way they pay attention or the amount of time they put into studying that makes them 3 higher than what I had anticipated. So my residual here, my epsilon hat, my estimate of my residual is 3. And adding that all together gives me my 41. So what we actually did was we purposefully put in a 3 so that we could get to what we observed. That's how we do it. We actually take what we predict, what we observe minus what we predict. Does that sound familiar? Isn't that how you calculated residuals from way back when we first started this course? What we observe minus what we predict. What I predicted was a 38. What I observed was a 41. So that monster's 3 more than what I would have predicted. If I go to the second monster, 42, and take away 4, for the being in the no concept mapping, that's a 38. And that's what that monster got, was a 38. And so the residual for that monster is 0 because they're right on what we predicted. So this model becomes a more realistic model when we have not just monsters with individual and independent personalities, but when we're dealing with human beings who have individual personalities. So that is a look at our very first model right here. This was for the one-factor design. Now note that I called it a one-factor randomized design here because we randomly placed monsters into conditions. But if we had observed monsters in existing conditions, if I had gone to a class where these monsters were here in the no concept mapping and I had nothing to do with that, and I found another class with monsters in it in the concept mapping and I had nothing to do with it, then I wouldn't call it a one-factor randomized design. I might call it a one-factor observational design or a one-factor non-randomized design, or just a plain one-factor design. So that design indicates how many elements we're going to have here, which include what's not included in the design out here as epsilon. And analyzing this is an attempt to estimate the factors of interest, which in this example is just alpha. That's the factor of interest. All right, we'll continue with this and look at some additional models for other designs in the next video.